Also, did you ever post a review file? Okay, so just review. Yes. And also the,
Morning.
probably bylaws.
You want the up there?
Oh, I just grab any chair.
Not sure why that is.
That's the chair. Okay, I see. Interesting. Thank you. I didn't see that one. Okay, so I was gonna call up question. Let's see if it worked. Okay, finally, when I came here, the projector is not what's on the computer, so I have to restart it. So on the board, we have a question. I think it's the same question like last week. But this is a question calculating the test statistic. So, you probably have some experience from the homework we did using the R. Same. Basically, ANOVA test allows you to figure out a relation between one quantitative variable and one qualitative variable. That one qualitative variable sometimes is being called a factor. So we have one way ANOVA or two way ANOVA. One way ANOVA is we have only one qualitative variable, one qualitative factor. And then the two way ANOVA is we have two qualitative variable and one quantitative variable. So basically, one way ANOVA or two way ANOVA, both are trying to compare the mean for different qualitative situations, for different qualitative category. So right, you should already be able to calculate the ANOVA statistics from using R, or you can also calculate it yourself. Basically, the ANOVA statistic is the F statistic is the variance within the variance between the groups divided by variance within the group. So essentially, that's the idea. So it's possible to calculate by yourself if there's no massive data. And in this question, we have four number for A, leaving 9, 7, 5, and 3, and then we have number 4 B, and they were 7, 7, 5, 5, and then there's C, three lowercase the 7, this one is the same. I mean, it's that much to data for C, data for B is the most calculated is F statistic. So we have four set of number, and if we want to do ANOVA test base R, we have to create this new data set format that include both the numerical variable and the qualitative variable. So C, X equals C, we're gonna try to connect them together, so then we go A, B, C, D. So this will allow you to put them all in the same data set. Run this code like this. You did your homework for for ANOVA, the 9394 all together test. You should kind of look familiar with this. So if you look at the X has 16 number. And we want to make sure every number is labeled by their qualitative factor. So we want to know if number is A or B or C or D. So you're gonna add one more thing that's called I just call that label. Label is equal to. So here we're gonna put in the name and the first 4 numbers from A. Label for every number for A. And there is for B. I think many of the calculator has similar function like R does. Relying on R for most of the computing, right? And we have B. There's 4 number that belong to the B data set. You know we're all set. So that's all the labels. So then we can create a data set. It's called a DAT, which you could data frame. We're using these as our we're going to turn a row vector into a column vector. So data frame will identify the value. The first variable is called the value, and then we use X as a first numerical column. And then we have the label. We're using this data set for the variable label. Those queried our data and our data. After we're done. It didn't work out. There must be some problem. That was an easy example. So maybe the way I use the function is wrong. I like to use equal sign all the time. I think it's a mathematics thing. Oh, we don't have data. We have DAT. It's the name that was wrong. Okay, so those are the newly created data set called DAT. So now we have our data set up properly. It's time to do the ANOVA test. If you do ANOVA, and we're going to try to find out how value is different between the different labels. So that's the goal for the ANOVA test. We only have one, the category is in the label. We don't have that multiple factor thing, so it's not a two-way ANOVA. It's one-way ANOVA, and there's only one data here. And then, of course, the data that we're using is what's in the DAT. Okay. If you run this, let's get rid of those extensions. I was just printing out these out, so it's going to be less output. So if you only run ANOVA, it will tell you this. So you can see I gave you the label, and I give you the residue, and I give you the degree of freedom. That's it. So it's kind of missing something. If you want to calculate, it doesn't tell you the F statistic. It also does not tell you the p-value. So if you would call the function, it doesn't have a lot of things. So you can save this outcome in something called result. It's supposed to be like save the test results. Supposed to be like results, but most of the time I make it short to RES. And then you can summary. to read everything that's in the RES. So we save the test result into a variable, and now you can lay it out with a data summary. And that'll give you more. And that's actually the end of the table. Okay. So I'm just trying to explain once again, how do we do ANOVA test on R? You can look at the section PowerPoint file to see how to do it manually. It's possible to do a calculation for the f-statistic by hand. This is only just one way ANOVA. Two-way ANOVA is a little bit more complex, but one way ANOVA it's possible to do it and you with the software. And that would be today's practice question. Just trying to review once again how we do ANOVA. Okay, let me collect your answer for the Flickr question so we can report today's attendance. It's the last day of the class. Wednesday is the last day. Tomorrow's the reading day. There's no more classes. So you saw my calculation. So the F statistic that we had. And so here. So that's the F statistic, and that was a p-value. And you can see the p-value is not small. So this is not significant. A smaller F statistic indicated variance with between group compared to variance within group. They're like 1.1. Pretty much means the variance between group is almost the same as variance within the group. That is saying that whatever variance or differences you observe in the mean between the four mean, it's kind of the same. It's caused by a natural differences between the number in the set. So that variance is not that much different than the variance elsewhere. So therefore, there's no true difference between the mean among the four. This will be today's attendance question. The answer is A, C. Today is the last day of school. Do you have any question you want to ask before? I don't have anything new planned for today. It's pretty much a review time. Any questions? The final exam study guide is posted on Church Review. So if you haven't really looked at it, you can take a look. And we kind of talked through it on Monday. So I don't have anything new to talk about today. Last day of school. It's in versus midterm solution to practice midterm. There's final exam study guide, final exam example question, and those are the solution for the example question. And then we did a couple of practice questions over the rest. And that would be more practice question. If there's no more questions, we could practice a few more. Actual question. Do you have any question? All right, so I'll go ahead and work on those practice questions. And this set is an example which follow closely to the final example study guide. So first question, given two distribution function, you can come up with the distribution of the x over y. So you know the distribution for x, know the distribution for y. Let's find out the distribution of x divided by y. And that's one of the questions that we study in section 5.2. The second question is, you can see we want to find out probability for x bar. X bar will be the sample mean. So second question is over central theorem. And you will calculate the mean from the density and calculate the variance from the density. And now you can apply central theorem to find out that if you had 18 number, what was the distribution for x bar? Then the third question is a maximum likelihood estimator question that belongs to a homework in 6.4. The fourth question was question about comparing proportions. Knowing proportion equal to 0.765 or not. And those are the data. And this is given 414 out of 600, we're going to calculate a new proportion compared to the old proportion. It's a it's a hypothesis test calculation. And then we have number 10 to compare before and after. It's a paired t-test. Number 6. This question asks for which test is more applicable. Like if you want to do parametric test, what you can do, and if we're comparing the mean, okay, so we want to test the claim, so we want to know which one's higher. A says my product is higher, superior, and then B says I don't think that's important. So we're testing whether A is bigger than B, I guess. So there's rebound height. So you look at the quality of the ball by measuring their rebound height. I guess the one that has higher mean should be assumed superior. So we would find out the mean for A and find out mean for B and compare them. So it's comparison for means. So in A, you should answer t-test. Does parametric test show there are two superiors? You're going to run a test for mean A bigger than mean B. We're going to test if that's true. And then C says, what if you want to do a non-parametric test? Okay, so if you're doing a t-test, you're assuming normal distribution in your data. And whether your distribution is normal or not, you may have to test your data to determine if it's normal. You can do the QQ plot to determine if it's normal. Then if it's not normal, what we can do to compare center of distribution will be the Wilcoxon test. So the answer for C would be a Wilcoxon test. And then in D, we will run a test. And then obviously the decision in CD, you would be compared with the decision on AB. So D would be which one? Like, what do both tests tells you? So what would be the conclusion for the t-test and what's the conclusion for the Wilcoxon test? This is something that we have done in, I think it's 8.5 for the Wilcoxon test. In the assignment for 8.5, these two, the t-test and Wilcoxon test, are being compared. So we kind of have to understand the similarity and differences between the two. I think I had a solution for this file. And then this question is comparing the mean. You have 3 brands. Compare whether they have the same mean. Example of a peanut butter produced by 3 different manufacturers. And we're trying to compare their salt content. Like which one has more salt, which one has less salt. So this is a NOVA test, compare multiple means. So as you can see, look through also to the assignment, you might want to like look at them and determine when would a certain test be appropriate. The solution for this set of problem has been posted, so I don't think we have to spend a lot of time on reading this. So those are the solution 1, 2, 3, 4, 5. That's page 1, and then page 2 is for the other 5 questions. So that's the solution I wrote earlier. And okay, so well, after learning this class, I guess we should be very familiar with many of the popular tests. If there's anything for any one learning statistics, the difficulty will be in what procedure do we choose for which scenario. So this is a couple of scenarios, or how do we choose the right procedure, the right action. And for example, this is the first question. Okay, so if we want to, which of the following statistical procedures, so we're choosing the right procedure, you are facing with a question. So let's say these are the data. We're trying to test the claim that students' overall course grade are the same in both courses. So we have AB and BC, 2 different AP calculus classes. Here we have those are the grades for students. if we're trying to find out, whether they are the same or not, what should we do? Which one makes sense, which procedure? It will be B. Okay, yeah, I think you are correct. A is a two-tailed, two-sample paired. It did say 5 students taking both classes. So it should be A, it's paired. So it's paired t-test. Now B is independent, saying that they have to be different students taking them. So there's no independency because the data are from the same student. Student 1, student 2, students 3 and 4 and 5. So because they are all from the same students, so there's relation between the two set of data, so it's not independent. So it should be A. Then B is wrong in the sense that it's independent test. C is wrong in the sense it says independent Z test. We can only do Z test for a smaller sample size if we know the population standard deviation. In this case, we do not know population standard deviation. Normally with real line data, we rarely have the population standard deviation, which is why t-test is a lot more popular than z-test. But that doesn't mean the test is not useful. For one thing, the test does not depend on the degree of freedom, and then it's a lot easier to run the z-test. So we definitely would want to run the z-test if we have large population. Like anything higher than 50, we definitely would prefer z-test instead of t-test, even if you are using sample standard deviation sample mean. Now D is one tail, two sample z-test. And that's even for proportion. So we're not talking about proportion, even though data being presented as proportion, those are grades. So this should be considered qualitative data. So it's not qualitative data, therefore we're not compare proportions. So let's just try to look at different procedure to compare which scenario apply which procedure. Now this is the second question. Value of the sample population coefficient. Right, a simple random sample of 5K race times for 30 competitive male runners age. Okay, so we have a mean value given for 32 data. The simple linear regression equation that fits the data is already given. The testing the claim that there's a linear correlation between the age and 5K race times. Okay. X represents the age, Y represents the race time. So Y is time, X is age. The claim is whether it's a linear correlation. So we're testing whether the correlation is large or not. I think this may be the one we skipped in the test of 7.6. That's where. So basically, correlation is a number that's between -1 and +1. So if the correlation is around 0, that is indicating no linear correlation. If the correlation is near 1 or near -1, that's indicating a higher correlation. Now here it even says we were given the test statistic and we were also given the p-value. So that p-value is really small, which indicating a strong correlation already. Proportional variation times can be explained by a variation in the age of the community. Okay, so now we have the proportion that's already given, and the proportion, this is not going to be one of our questions because we skipped the 7.6, but you guys have elementary statistics in that class, we did mention about the correlation and variation explained by the relation represent R squared. So essentially, the question here. We can actually identify key information from the question already being given here. So we got a test statistic. We have a p-value. And we have a proportion of the variation explained by the relation, which essentially is the R square. R square is 0.663. And you can see that the relation is also given, right? And that coefficient being negative, that indicating R is negative, right? The coefficient of the linear equation, this we learned in 6.5, that this coefficient is actually equal to correlation multiplied by standard deviation of y divided by standard deviation of x, which then is equal to the negative 0.276. Okay, that's the reason that we see the correlation is negative. In our book, in this textbook, we use a rho for the correlation, but in most of the elementary statistics book, we use R for the correlation, but essentially, in this case, R is negative. So the R value, the correlation would equal to negative square root of 0.663. Right, because we're here, so we'll just explain the logic behind it. So you can see because of that coefficient, it's negative, it has to be a negative correlation between age and time. So we should have the C would be the answer. It is negative square root. Negative square root of, this is actually a percentage of determination, correlation of determination in R squared. Any question? Okay, again, this is not gonna be, it's not on our study guides. We're not focused on this, but it's kind of worth mentioning that correlation between two variables is one of the questions that we study in elementary statistics. Now, the next practice question goes 160 students who were majoring in either math or English as a test question. Whether they answered it correctly or not, the response and major are independent. So here you see a table, and we see that the accuracy for a math student, the accuracy 160. So there's 80 students here. 27 plus 53 is 80. So this table, I think it's kind of like a table for the frequency, right? It's qualitative variable. And so ask a question and then we determine whether it's correct or not, whether they answer the question correctly. So correct or incorrect, that is the accuracy. And obviously it's qualitative, right? Yes or no, right or wrong. And then the major is math or English. So whether math major or English major, that's also qualitative. So essentially what we have here is a contingency table right there. That's the frequency, right? So essentially we're looking at a relation between the proportion. So normally I would recommend calculating the chi-square test. The chi-square test is when you try to handle multiple proportions for multiple qualitative variables. But in this question, we're trying to find out 98% confident interval for percentage correct in the math student and percentage correct in the English student. So essentially you're looking at subtraction of two proportion, right? So it's like a proportion test. So we don't have to do the chi-square test because we don't have that many. Okay. If you want to do this, you can do a chi-square test to determine if they have the same proportion. If they have the same proportion, that will be indicating that the major and accuracy are independent from each other, meaning that they have the same proportion. That's the meaning. if the chi-square test indicated no relation or independency, proportion would equal to each other. But then you can also do the confidence interval for the proportion. If this proportion is not equal to 0, that means they don't have the same proportion. That means that one major has lower success rate. And that means whether you have this major or that major affected how accurate your answer is, right? So then that's the connection between the two kind of tests. Chi-square tests try to figure out independency between the qualitative variable when there's null hypothesis in the chi-square test, which is the claim that the proportion are the same for different category. And proportion test compares specifically proportion, but if the qualitative variable are independent from each other, we would have the same proportion. So run the proportion test or run the chi-square test should give you a very similar result, as long as we kind of know how to do it. So if we were to do the calculation of the percentage correct for math students, I guess the proportion is already there. The proportion of correctness is right there. And you know how to calculate the math students, it will be out of 80 students, the correct is 27. So 27 over 80 is for the math major. And that's how you get the 0.3375. And then for the English major is 43 over 80. That's why you see a higher percentage. And then essentially we're subtracting this proportion for this. That's the point estimate for the proportion. And then you have to use all the numbers to come up with your 98% confident interval. Now we haven't do a lot of that, but you can follow that. So essentially we have number of success in the first one. The mass is 27, and then the sample size for the math student is 27 plus 53. There's 80 students, right? For the English major, we have X2, the number of success is 43, which is out of 80 students as well. 43 plus 37, right? We have a total of 160 students. So then the proportion, I'm not doing more notation, I'll just do P1 equal to X1 divided by N1, and then P2 would equal to X2 over N2. Are you okay so far? So I'm calculating the confidence interval manually. And what are the calculations? So it's going to be P1 minus P2. That is a point estimate. And we should be doing minus the margin of error and plus margin of error. So that will give you the confidence interval. But we also should calculate the margin of error. In the proportion test, margin of error is equal to Z times, we use V times square root of, I don't know if you remember, it was P1 times 1 minus P1 and divided by N1. That's the variance for X1 over N1. And then there's P2 times 1 minus P2 divided by N2. And for this, we already assigned the value for T1, Q1, N1, N2. We haven't really assigned the Z. Z is the confidence interval, critical Z for 98%. 98% in the center distribution, that means 2% on the outside. That means on the lower and upper tail, there's 1%. We need Z is from the normal distribution, so 2% on the 0%, 0.01, either tail, left tail, right tail. Normal distribution do not need a degree of freedom, and this is going to be a cumulative distribution for 1%. This is going to give you a Z, so you're going to want a positive, so negative. And I think that should get everything ready for your final calculation. So this is going to pump them into R. So that's one of the example that we did for homework. A 7.3 proportion test, confidence interval for proportion. So there we go. Calculating the point estimate for both proportion, subtract them to get a point estimate and then figure out the confidence interval, the margin of error, margin of error for the confidence interval. Here we go. That will be the confidence interval. And you can see they're both negative, which is a clear indication that the correct, the accuracy percentage is lower in the math student compared to the English student. Depending on what was the question, but specifically we compared the portion, and that will be how we answer that question. All right. Of course, if you want to do it with R, there's one language called proportion.test. You're going to provide your X value. In this case, X value is 27 and 843. Those are the number of correct answers. And then we have the N, which is giving a vector of 80. All right, we should also put in the confidence level. Hope I type it right, which equals 0.98. And that should also give you. And also we should indicate that we don't do any correction of continuity. So that should be false. I want a computer to do automatic change for. So that should be unless my confidence was. All right. So 98% confidence, 98% confidence is also part of the outcome, even though it's still in a proportion test. You see the p-value. That is definitely a small p-value. So the test result is significant. So it's smaller p-value, so we know that the two proportions are not equal. That's the same confidence, right? As the manual calculation provided the identical results as we have in the test. So this is definitely a quicker way to get all of things calculated, but I want to show you to do both ways. If you are short on time, and make sure you have everything set up right. I kind of review the proportion test. The next question asking for is another proportion test. Random sample 223, and then the yield 90. So sample size is 233. The success is 98. When I calculate that proportion compared to the 0.34. And can run the proportion test or do it yourself. Any question? So the calculation is actually slightly different. And this is a one proportion, unlike the one we did before, it has two proportions. I guess we don't have to do it. Are we okay? This one, there's only one proportion, so Z is going to equal whatever proportion you have, P times. What is it? V is multiplied by the portion that we have, which is 96 over 233. That's the point estimate for the proportion. We're going to minus the proportion in question, right? In the hypothesis, P hat minus the P0 divided by square root of here. You're going to have the proportion of success in the null hypothesis multiplied by 1 minus 0.34 and divided by the sample size. The sample size is actually 232. That's the calculation for Z, depending on whether Z is higher or not. All the Z is already given. So all we have is state the conclusion then, right? Let's see if we are getting the same Z value. Let's see what that Z value is. I guess this is it is 2.32. So I was gonna do it, then I realized that everything is already in there. So test takes 2.32 is really high. The p-value is 1%, and then the alpha is 5%. So that's definitely significant because p-value is smaller than alpha. So our conclusion will be we do have sufficient evidence to conclude that the Littleton in Littleton, the proportion is higher than 3/4. So you would, when you try to state your conclusion, you repeat the question, but in a negative or positive way, depending on your test result. In this question, it's significant, so it would represent yes, the data did provide sufficient evidence for the conclusion. That's how we interpret the result. And of course, the test, we could run the test procedure ourselves, but it's already done. So in this case, we don't have to do it. And number 5 has 16 men, 13 women. These are rate recorded for. These are pulse rate, different population. And assume a doctor wanted to test the distribution of pulse rates differ for men and women. Okay. So if we have qualitative data, in order to determine if distribution are the same, we would be doing the chi-square test, right? But if you are already, you know this is quantitative data, I think we still would recommend doing the independent t-test. We have a quantitative for male and quantitative for female. Obviously, being one has sample size 16, one has sample size 13, that's independent. It's definitely not paired. If it's paired, they would have the same sample size. So the null hypothesis will be they have the same mean. The alternative will be it says differ. So the alternative will be a two-tip test saying they don't have the same mean. And as far as quantitative data, the main concern will be the mean. So if you want to compare this quantitative data and that quantitative data, are they different or not? I think all we have to do is look at the mean. If you want to compare more of the quantitative data, you can compare their variance. And that's it, right? If data have the same mean, the same variance for quantitative data, that's enough to say they pretty much have the same distribution. Is that okay? All right, and then of course, if you want a more specific, want to compare their distribution, I guess you will look at the histogram and to say if they kind of shape the same way. Like maybe one is triangular distribution, the other one is uniform distribution. That is when you have more data. With this being only 16 data and 13 data, we don't have a lot of information to look at the graphic display of the actual distribution or the actual histogram. When we have more data, we could look at the more detail. Are they symmetrically distributed? Do we have null distribution, t-distribution, that kind of thing? This question, I think compare the mean will be sufficient. And then figure out the mean for each one, do a hypothesis and t-test, and calculate the test distribution. The procedure. Any questions so far? We're just reviewing question to prepare for the final exam. On the final exam, we will have Wilcoxon test, we will have paired t-test, we have the ANOVA test. So those are targeted procedure we cover. This is a question calculating correlation. And correlation, I think I mentioned the formula there. Well, skip it. The correlation between two quantitative variable is equal to rho. That's correlation. Rho is equal to the covariance. I guess we talked about this in chapter 4. Covariance of these two variables divided by square root of the variance x times variance y. But then we also have a formula for its computation. If you want to use R to help you with your numerical calculation, you can enter the data. And I think the correlation function is COR, and that may be a little bit faster than doing the correlation by hand yourself. Any question? Okay, so that was the formula that we're using in chapter 4. But we don't have to do that. I think it's not that difficult to do it either. But we are calculating it with assistance from the computer. You will be entering all your number for X. Skipping that part, and then enter the data for Y. And then the calculation will be COR X Y. That's how do we calculate correlation in R. And then correlation itself, the calculation is not as important as understanding of it. So if we use R, which is a calculated correlation, it will be a number less than 1, bigger than -1, right? If it's negative, if R is negative, that means these two data has negative correlation. If R is positive, that indicating positive correlation. Now, if R is almost 0, that indicates these two does not have a clear linear relation. Number 6, just want to explain how to calculate it. Number 7, we were supposed to run ANOVA. Well, the ANOVA is done. We will try to understand it and see. And that's more of a question that we were doing in our statistics class when we studied the procedure. So here we have an ANOVA table that has some missing data. So the question says that let's try to figure out the number A, B, C, D, E that was missing in the chart. Okay, start with the A. And you can see A is a summation of square. And we have to understand the relation between all three numbers, right? So basically the summation of square divided by, find somewhere that's a little easier to type. So basically the summation square divided by the degree theta in that row would equal the mean square. So that 3 number is indicating that if you take the A divided by 3, you would be getting 18. So understand that relation. So we kind of know that A is equal to 3 times 18, which that is 54. Okay. So from that relation, we figure out that this is actually going to be A equal to 54. Small. So once we know A, we can look at this relation now, because the summation squared has its fundamental relation. That is the total summation square. It is the total summation square, because we have this relation saying A plus B would equal to the total summation square of 162. Now that we know that A is 54, so we can calculate B, which equal to 162 minus 54, which B minus 10, 808, right? Let's subtract, yeah. So now we have the B. B would be 108. So back there we fill that number. Okay, would be. So this exercise kind of made it easy for us to figure out the relation to all these quantities. So that one we can move on to another relation, such as this rule. We already kind of see how things are related in the first rule. Second rule have a similar relation. Now that we already know the B, realize that B divided by 15 will equal to the D. That's the mean square. Since we already have B equal to 108, so 108 divided by 15 B. And what is 108 divided by 15? Find out what that number is. 7.2. So the D is actually 7.2. Okay, so the mean square represents variance between and variance within. And to calculate the F, this number, okay, you're gonna really look at the relation between the three, that's this three. So F is equal to variance between divided by. So F is equal to mean square variance between, which is 18, divided by the variance within. That's the D representing mean square that's caused by error, like a natural selection error. So that's going to be 18 divided by 7.2, which will allow us to find the F statistic. Is the last portion of the calculation. Okay, at 2.5. So F statistic 2.5. And then we will be finishing up any calculation necessary. 2.5. The F. And we will have numbers on all the big state, one state, and the one three. Any question? All right, so this is one of the examples that provide a little bit of understanding for the ANOVA table. And now this question is an experiment designed to compare the length of time for 4 different drugs providing pain relief. And so we're comparing this relief time for 4 different drugs. So which test are we supposed to do? If we're comparing 4 medicine. ANOVA. So we should be doing ANOVA for this. And then I think we had quite a few exercises to do ANOVA. So then so basically you have all the quantity entered, attach every quantity with a label, like this is A, this number is from B, this number is from C, right? So your label would be like A, 4 of them, and then B for the next 4 number. And then you're gonna have 5C and then 3D. And then add that label onto your numerical variable. So you should be creating the data set that has 2 columns. And we'll do the ANOVA test. So based on the F statistic, you can determine whether there's evidence to say that are different. I think they're different. You can see D obviously has a higher mean, and C has a higher mean, and D had much lower mean. The other two are not very easy to compare, but C definitely is kind of more than all the other ones. But we have to run the test to know whether it's significant. And 9 is a data set about what we're talking about. See if it's qualitative or quantitative. Assembly process also determine whether the number of defective part manufactured depends on the day of the week. So we want to know if the day and the defective part, non-defective part are having any correlation, right? So we're looking at 2 qualitative variables. One is Monday, Tuesday, Wednesday, Thursday, or Friday. Those are the day, right? That's qualitative. The other variable is now for every part, you want to understand, is it defective or is it non-defective? So essentially, we want to know whether defective or non-defective as a property is being affected as the day. So does any days has more defective part? That's the question. It does look like Monday has more defective part than all the and then the Wednesday, Thursday, but we don't know if that's significant enough to say anything. So how do we do this? Like, how do we make comparison? What kind of test is like meaningful? So a chi-square test. So I wonder if you have done your homework and kind of be familiar with how do we do chi-square tests. So if we have time, try to start from the beginning. If we use R for the computation, we're gonna throw this whole charge into R and let it run the chi-square test procedure. We can do the chi-square manually. Let's take all the frequency minus the expected frequency square and divide it by the expected frequency. That is 1 chi-square. And then we got 5 for the non-defective on Monday, Tuesday, Wednesday, Thursday. And then we also have another 5 for the effective part frequencies. Essentially, we have 10 number to do in our chi-square calculation. So it's a little bit lengthy. So how do we let the computer do all the work? We'll have enter the non-defective part. Let's call that non-B. We're gonna enter all 5 numbers. There's we don't have to enter the total, column total or row total. They don't belong to the actual frequency. They belong to like a summary data. So we put in the 36 and then 38, 38, and maximum 36. So those are the frequency for the non-defective part. And we have the defective part. I'm trying to randomly label them. And then we have 6 and then 4, 2, 2, and then 4. So those are. Okay, so what we're gonna do is really combine them into a table. So essentially, we're entering the entire continuous state table into R, and then R does the rest of the computation. Okay, so then, and then we're gonna combine them. One is the top row, and then the other one is bottom row. So we're not gonna link them together to one vector. We're gonna let them stay as 2 separate vectors, make a table. So we'll just call that table, which equal to, we're combining the row as row. So we do R bind, which is combining row in. This is gonna be the first row. It's gonna be the second row. After we do that, you can look at how it looks like in R. And that's gonna be our input data in the chi-square test. So if you do this, I'm printing out the TAB, which is really meaning table, printing out the table for us to see what is being entered. So that's kind of like a very similar table, except I didn't put the title in, and the computer automatically assumes that's your notation for the first column, second column, third column, fourth column, and fifth column, which could be our double as our Monday, Tuesday, Wednesday, if you want to identify the day. And then those are the row name. Variable. Okay, so kind of it's a way to create a table that you can throw into the chi-square test. So we're gonna do a chi-square test and just give in that, and then you're pretty much letting the computer do a calculation, and it's going to tell you what's the chi-square. Right, Pearson's chi-square test. You can see the chi-square, the degree of freedom. We got 5, and therefore 5 minus 1 is 4. Freedom 4, that's a p-value, and that p-value is high, which indicating that there's no significant difference, even though they do look like, say, 6, 4, 2, 2, 4. That's a defective part, but statistically, the difference is not significant. All right, so that does not show a lot of information. So if you want to see more of the result in the chi-square test, you can do RES, which is saving the result. Now you can do a summary to show something similar to the unknown table. Okay, and now you want to print out the result in more information is displayed. I guess there must be something that I didn't know. It's not. What did I miss them? This is print out the explanation, but it's not a lot. Okay, anyway, I think it's because the table does not have a high number. There's only 2 rows. If we have more rows, there might be more information. I guess we don't have to do this. Anyway, let's draw the conclusion for our chi-square test. So based on the chi-square result, we know that the chi-square is not significant, and p-value is also bigger than alpha. So back to the question, we say that the if you want to determine whether the number of defective parts depend on the day of the week, the answer it would be it does not depend. So what we're doing is a test for independence about the number of days, the days the type of days and the number of defective part. They're independent from each other. Therefore, pretty much we have the conclusion that the percentage of defective part for Monday, Tuesday, Wednesday, Thursday, and Friday are the same. Right? That means they're independent. These two things are independent from each other. So the number of defective part does not depend on the day of the week. So if it depends on it, then we would have a smaller p-value. We'll be indicating, hey, the proportion are not different. Remember the chi-square test, the reason for the chi-square test is comparable to proportion. Like on Monday, what was the percentage defective part? On Tuesday, percentage defective part, and Thursday and Wednesday and Friday. And then if you get a high p-value, it's indicating that there's not much of a true difference. I think we've done all the 9 questions in this file. Any other questions? So I'm trying to present a couple of scenarios for how question can be asked. Essentially, according to our study guide, we want to be able to do determine the distribution, use central limit theorem to find probability. That's what we've had a couple of practices in the quicker question. Maximum likely estimator is assignment from 6.4. Test for independence is the one we just did, like the one for the number, day, and defective part. Paired t-test is the one we were talking about, and before and after. This is the paired t-test. The other one is before and after. Before and after. No, I think it's in the other file. In the other set of practice question, the test for proportion, we tried it together. That's assignment from 3.4. Linear regression determining alpha, beta, and sigma. That was assignment from 6.5. If you're a little bit beefy on how do we determine the equation from the question, you might want to review your homework on 6.5. Real Coxon test is on 8.5, and one we ANOVA is 9.3. Or 9.3. Those are the planned type of question. If there's anything that we haven't practiced enough, is this one. If you have distribution for X and distribution for Y, how do we find distribution for X over Y? Let's see. We have assignment. We have 5.3. This felt like one of the questions in 5.2. I feel maybe we could switch that question since we had not had the assignment on that section. So for chapter 5, let me switch out that question for one of those questions in 5.3 instead. So the first question, instead of doing this, I feel like to do this, you have to review a lot of content that we did in 5.2. Instead of relearn 5.2, let's make it a question from section 5.3. That's our first assignment. So given the distribution for X and Y, we should be able to find the distribution for a random variable of X and for a sample of size and I can't specify. It could be 4 or 5 or 3. We should be able to identify the probability distribution for X1 plus X2 plus X3. So that's something that we practice in 5.3. So instead of, let's make it side 3. Is it okay? So that way we can relate better to 5.3 instead of moving way back to 5.2 stay as far as 5.3 would be. Change the study guide question, and that way you don't have to study the first question on the example file. Instead, using your 5.3 homework as a exercise. And for that, you can also use the moment generating function to. Oh, okay. Excellent. Any question?
So the test will be follow similar to this.
Right, so this will be the plan for the test. So it will be a better idea to not have to study a lot of past review from 4701. So instead, we focus on this semester. Any question? Any question? All right, it's 12. I don't feel like there's a lot of things that we need to talk about. Because we were reading through all the final exam question, I realized the first question looks like really way past what we were doing this semester. This semester we started with 5.3, and then we went on with 5.4, 5.5, and then we finished chapter 5, and then we did chapter 6. So we did not do the 5.2. That was the last section that we were talking about before. And that was the one of the section that we covered in 4701. So let's move on that section. I guess we can pull one of the example for 5.3. We have a little bit of time left. 5.3 focus on independent variable. If you have another distribution, you have a couple of sample from it. How do we come up with a distribution of several variable? That's the focus for 5.3. We also learn moment generating function. So kind of like 5 and 6. In an example for this. Those are okay, especially the question 5 and 6. It could be example how do we determine the distribution when you have a summation of two variables. But then 5, 4, 4. Like it. So kind of like the number 1, you have 3 variable y equal to summation of all 3 variables, study the distribution of it. And that's one question in 5, 4. And then this one is trying to find out the distribution for x1 plus x2 plus x3. And one thing we should remember is that if x1, x2, x3 are all from Poisson distribution, then the summation will also be a Poisson distribution with a bigger mean. Okay, so let's look at number 7. Pretty much try to review the idea that if you have a distribution for one variable and then you got a random sample for that same distribution, what should be the distribution of a summation? So this will be a good example on knowing the distribution for a random variable. And then you got a random sample from that distribution. What will be the distribution of that big summation? Do you remember how do I solve this question? Let's by 4, right? To answer that question, what we did was use the moment generating function to understand the distribution. So if you got the moment generating function, that gives you indication of the actual distribution function. And when you know the distribution function, it's not so hard to find the density function for it. So that was a gamma distribution. The gamma distributions MGF. I wonder if you remember it. The MT, which is equal to 1 over 1 plus theta t to the power alpha. Any question? Okay, so that was back in the moment generating function was section 3.2, right? And then if you have the moment generating function, realize moment generating function is calculated using the expectation of e, suppose the variable is x, e to the t times x, right? A calculation of the expectation is integration using the variable x. So the e of e to the tx, the e itself cancels out the x. So that's why our function results only have t as a variable. There's no more x because e is a averaging action. All right, and therefore, if you want to calculate the moment generating function for y, essentially for like m, y, t, you will be calculating expectation of e to the t, y. And then y is equal to summation. So this is the expectation of e to the t times x1 plus x2 plus x3. Now, this is a t time. You distribute the t, and then we have e to the expectation of e to the tx1 plus tx2 plus tx3. But then summation in the exponent for exponential function is essentially multiplication. So it's e to the tx1, e to the tx2, and then e to the tx3. So that's the moment generating function calculation, still theoretical. But then we realize this is a random sample. In a random sample, all the variables in that sample are independent from each other. So x1, x2, x3, they're independent from each other. So this is equal to e of e to the tx1 times, it's due to independence, e to the tx2, and then e to the tx3. But these are all x variables. They have the exact same moment generating function. So essentially, this is equal to mt times mxt, and then mxt. So since they're from the same distribution, this is really mt cubed. Now we want to double check what's our MT. It's from the gamma distribution. So MT is equal to 1 over 1 plus 5t to the power 7. That's MT, right? And we're gonna raise this to the power 3. So it's gonna be 1 over 1 plus 5t to the power 3, and there's a power 7 there. So 3 times 7 is 21. Okay, right? And then we realize there's a one-to-one correspondence between the moment generating function and the distribution itself. This is the moment generating function for a gamma distribution. So this is gamma distribution with variable, with coefficient parameter of 7 and 5. Okay, alpha equal to 7, theta equal to 5. And now what we have here is, you see we still have the 5. So in this case, y follow the variable y that we're trying to determine. It follow a gamma distribution. The follow, right, here that follow gamma distribution with parameter 21 and 5. Theta equal to 5. Okay, right? So instead of 7, 5, now we have 21, 5, all because it's a summation of 3 gamma distribution. And I kind of draw one of the conclusion that we had in 5.4 is that summation of several gamma distribution is a bigger, another new gamma distribution. And then from knowing the distribution, if you want to, you can write the density function, right? Density function will be gamma distribution, I think it's 1 over x to the power of 21 minus 1. And then e to the negative x over 5. And that was the gamma distribution. Then you're going to have a gamma of, I think it's gamma alpha, it was like 21. And then theta to the power of, theta is 5, to the power also alpha minus 1, I think it's 20. Right, so you can rearrange all the other coefficients to fit the density function. But normally we're not required to write down the density function of the gamma distribution. All we have to know is knowing the proper coefficient. Any question? I hope that's okay. That was one of the assignment, one of the homework exercise on 5.4. There are a couple other similar questions. And you see the 6 is similar. It's from a geometric distribution. We're trying to find the distribution of the summation. There are other questions, nothing kind of setting. The 15 is knowing one variable, and then y is a summation of 5. And so if you need a more practice question for the first one, then you can find plenty of them in the homework assignment. And all you have to do is make sure that you do your homework for 5.3 and 5.4. Any other questions? Any questions? I'm trying to go over any possible concern or a problem that we should fix for the final exam. Our actual exam, I think I labeled the date is the final exam date is May 7. May 7, 10:15 to 12:15. Any questions? If there's no more question, that should be it for today. But if you have more questions, feel free to type them here. And I will be here most of the, before by the final date. Yes, if you miss a attendance, if you're absent on certain day, you can let me know your answer to the clicker question. Like just label like April 21, and the answer is A or B or D based on your understanding of it. And then I can check if your answer is right. And then knowing the answer to the clicker question probably means you watch the video of that day, and that counts for your may counts for the attendance. Any other questions? All right, if there's no more question, that's it for today. And please get ready. And then in the meantime, I'm here on campus most afternoons. I should be in my office at 233 on most of the afternoons. some of the days, like May 6 and May 7, I have to proctor the final exam in the morning. But I should be free most of the afternoon. So if you need to see me or ask questions, you can easily find me at my office during the afternoons. Like 12 to 4. And then I normally will leave after 4 o'clock. But if you need to meet me at any other time, I will try to be available. As you say, I try to stay on campus. Whenever you want to find me, you should be able to find me. But if you have any question or concern, feel free to contact me. And that will be it for today.
So you'll be up there till 4 today as well.
Yes.
Just.
Any questions? And that should be it for today. I'll see you on campus. Feel free to stop by. Let's try to get ready, make sure all your classes is finished successfully. I'll see you around. That's it for today. All right. Thank you.
Just wondering, creeping up on that last question on 6-8, you said would be.
The 6 to 8. Yeah, I will be on campus. I'll be in my office. I'll see you around.
Yeah, I'll be by later today.
Mhm.